Simplifying non-perfect square radicands. Here's a review of simplifying perfect squares. A number is a perfect square if you can take that quantity of 1 by 1 unit squares and form them into a square. 4 is a perfect square because you can take 4 unit squares and form them into a 2 by 2 square. Notice that the square root of 4 is the length of one of its sides, since that side times itself equals 4. So the square root of 4 is 2. But what about numbers that are not perfect squares? How can we simplify the square root of 8? 8 is not a perfect square, and no matter how we arrange the square units, we will not be able to form them into a square. So we know that we will not have a whole number, which we can multiply by itself to equal 8. What happens when the radicand is not a perfect square? Rewrite the radicand as a product of its largest perfect square factor. So the largest square that's in here is a 2 by 2 square. So we can rewrite the square root of 8 as the square root of 2 times 2, which is 2 squared, times 2. Simplify the square root of the perfect square by taking the square root of 2 squared. Remember, if you take the square root of 2 squared, you get 2. So the 2 moves right out front. When the simplified form still contains a radical, it is said to be irrational. So this number is irrational. So once again, we're going to rewrite the radicand as a product of its largest perfect square factor, then simplify the square root of the perfect square. Okay, so 125 is 25 times 5, correct? Did we all agree on that? Okay, 25 is 5 squared. And then we still have the times 5. And this is all under the radical. The square root of 5 squared is 5. So that moves out front, and what's left is this square root of 5. Once again, when the simplified form still contains a radical, like it does here, this number is said to be irrational. So once again, we can say that 125 is 25 times 5, rewrite the 25 as 5 squared, then we take the square root of just the 5 squared, square root of 5 squared is 5, move it out front, and we have this 5 left over under the radical. Identifying the largest perfect square factor when simplifying radicals will result in the least amount of work. So for example, if we want to simplify the square root of 32, 32 is 4 times 8, and 4 is 2 squared. So we take the square root of the 4, bring the 2 out front, and we get 2 times the square root of 8. But this isn't fully simplified, so we have to keep going. So 8 is 4 times 2, so we have a 4 in there, which we can rewrite as 2 squared. Take the square root of it, another 2 moves out front. So we get 2 times 2, and we still have that 2 here that's left over. 2 times 2 is 4. So the answer, the fully simplified answer, is 4 times the square root of 2. However, if instead we find the largest perfect square factor, it's less work. 32, we didn't have to say that 32 was 4 times 8. We could have said it was 16 times 2, because 16 is a perfect square. That way, 16 becomes 4 squared. Take the square root of that, and you get 4 out front, times what's left, the square root of 2. Note that the answers are the same for both processes, but this one took less work. Another method for simplifying non-perfect squares is to use prime factorization and a factor tree. For example, 48 can be broken down as follows to find the square root of 48. So 48 is 2 times 24, 24 is 2 times 12, 12 is 2 times 6, and 6 is 2 times 3. After factoring the number into all of its primes, circle each pair of numbers that exist to signify that they come outside of the radical. So here you can see we have 2 2's, so we circle them. We have 2 more 2's, so we circle those. The below calculation shows that for each pair circled, one number comes out. Any numbers left without a match, like this 3, must stay inside of the radical. Multiply them together if needed. So you can see square root of 48 can be rewritten as 2 times 2 times 2 times 2 times 3. And anytime you have two 2's, they become 2 squared. And this also becomes 2 squared. And whenever you take the square root of 2 squared, you just get 2. So the 2 moves out front, so does this one. The 3 stays behind. 2 times 2 is 4, so we get 4 times the square root of 3. Try these. Alright, so we're going to write the prime factorization trees. For 72, 72 is 2 times 36, 36 is 2 times 18, 18 is 2 times 9, and 9 is 3 times 3. We have a pair of 2's, so the 2 comes out front. We have a pair of 3's, so the 3 comes out front. And we have 1 2 left over, so it stays under the radical. 2 times 3 is 6. The 2 stays under the radical, 6 times the square root of 2. The square root of 18 is 2 times 9. 9 is 3 times 3. So we have 1 pair of 3's, so therefore a 3 comes out front, and we are left with a 2. So that stays inside the radical, 3 times the square root of 2. Over here, 360 is 2 times 180. 180 is 2 times 90. 90 is 2 times 45. 45 is 3 times 15. 15 is 3 times 5. We have a pair of 2's here, so the 2 comes out front. We have a pair of 3's, so the 3 comes out front. We have a 2 and a 5 left over, so both of those stay under the radical. Then to simplify, we just multiply them together. 2 times 3 is 6, 2 times 5 is 10. Finally, we have the square root of 24, which is 2 times 12. 12 is 2 times 6, and 6 is 2 times 3. We have 1 pair of 2's, so the 2 comes out front. We have a 2 left over and a 3 left over, so both of those stay under the radical. We multiply them together to get 6. If a radical begins with a coefficient before the radicand is simplified, any perfect square that is simplified will be multiplied by the existing coefficient. So for example, 18 can be rewritten as 9 times 2. 9 is 3 squared. Therefore, 1 3 moves out front. There's already a 2 there. So we're going to multiply those numbers together, and it becomes 6 times the square root of 2, which is left over. 7 times the square root of 12. 12 is 4 times 3. 4 is 2 squared. So a 2 is going to move out front. It's going to multiply by the 7 that's already there, and we're going to get 14 times the square root of 3. Likewise, if a radical begins with a coefficient before the radicand is simplified, any pair of primes that are circled will be multiplied by the existing coefficient. So just like we just did, 2 times the square root of 18, 18 is 2 times 9, 9 is 3 times 3. This is exactly what we had on the last slide. So we get 3 squared, so a 3 moves out front, but there's already a 2 there. So therefore, it becomes 6. And here, 12 is 2 times 6. 6 is 2 times 3. We have a pair of 2's. Therefore, 1, 2 goes outside, multiplies by the 7, and becomes 14. Express -3 times the square root of 48 in simplest radical form. We previously simplified the square root of 48. It's 4 times the square root of 3. We did this on a previous slide. So therefore, -3 times the square root of 48 would be -3 times 4 times the square root of 3. So therefore, we multiply -3 by 4, and we get -12 as our coefficient times the square root of 3.